And so I think we can start. So let me change screen. I invite to this stage Dr. Florian Gahbauer. So while he prepares and share the screen, let me introduce him. So he is a researcher at the Laser Center of the Faculty of Science and Technology at the University of Latvia in Riga. So he received his PhD in physics from the University of Chicago with a dissertation regarding measurements of the composition of cosmic rays at the energies at around 1 tera-electron-volt per nucleon using a balloon-borne particle detector. So after his PhD, he switched field to atomic physics, and in Riga he studies coherent effects in atoms involving interaction with polarized light, magnetic or electric fields, and their hyperfine structures, the hyperfine structure of the atoms. He also applies similar techniques to nitrogen vacancy centers in artificial diamonds, and in both cases he's also interested in applications to magnetometry and quantum sensing. So please, Dr. Gahbauer, the floor is yours.
Great, thank you very much. Thank you very much for the invitation. It's a pleasure to join you. Can you hear me, by the way, and see the presentation? Okay, great. So yeah, as you heard from the introduction, my background is much more experimental, but here we try to always do experiment and theory together. So I try to learn theory also. So that's what we'll be talking about a little bit. And let's see, oops. Okay. So this talk is going to be based on an article that we published this past year about a toolkit, which you can then also find on Github if it's useful for solving the optical Bloch Rate equations in alkali metal atoms based on quantum optics package in Julia, which is a language which may not be so familiar to everybody. It's well, I'll talk a little bit about it later. So the outline of the talk, as you can see here, is first of all, I'll talk about what kind of systems we want to model, why Julia, and then I'll give some simple examples. So I understood it should be simple, so I tried to keep it simple. I hope not too simple. Then what we can do with magneto-optical signals in cesium vapor, and an unexample, let's say, I think Francesco asked me. So we'll see how that goes. So here's our typical situation that we're trying to model. It's pretty standard, been done for decades. A vapor reference cell with usually cesium or rubidium. We have a magnetic field, usually of arbitrary direction and strength. Occasionally we use electric fields. And then we have a laser beam of arbitrary polarization, linear or circular, and the vapor inside, and the atoms leave the beam at a rate little gamma, and of course new atoms come in, but we assume that the new atoms that come in before they return, they have collided with the wall and therefore have relaxed to the ground state. So the atoms that come in have relaxed to the ground state. That's something you could mitigate if you had paraffin coating on the walls. We don't currently have such cells, so we're not worrying about that, but actually we want to get a cell like that soon, so we'll be worrying about that. So the first question is, why Julia? Yeah, it's a relatively new programming language from, well, 2012, not that new anymore. And the promise sort of was as easy to program as Python and as fast as C. And well, I think that's somewhat successful. It's gained popularity, perhaps not as quickly as people have hoped. Anyway, when we started this, yeah, we did want to try to do it. It is not object-oriented like Python or C, which may be maybe a disadvantage, but it does have multiple dispatch, which is very nice. So that means you can define a function and one name can perform different tasks based on the number and type of the variables. So that's cool, and it's open source, of course. And well, here's sort of a relatively old benchmark plot where you can kind of see what's going on. So here C is always the reference for various tasks that are listed here. And you can see Julia tends to fall in the same order of magnitude as C. Some other languages that are faster, like Rust, but it's still on par with Fortran, and Python. Well, it depends. Python can be very fast, or it can be up to an order of magnitude slower. So it depends a little bit on the task and how it's done. And it's easy to parallelize. Also, and that's very nice. Just like Python, it can be used in Jupyter notebooks. So in that sense, it's easier to play around with, or to use in a course or something like that. And this is the package that we use for the quantum stuff. It provides. It's inspired by things like Quantum Optics Toolbox for MATLAB, or the Python framework QTIP. And it provides basically a lot of variables and tools for quantum physics that make the code cleaner. Obviously, we know we can do everything with matrices, and we don't need anything else. But and that's true. But this puts a little bit more order into everything. And yeah, here's the alternative QTIP, which some of you may be familiar with or not. Certainly, it's been around longer, more mature, has a bigger user base, many more examples, entire courses based on it. And being Python, it's object-oriented, and everybody knows Python more or less. Whereas the Quantum Optics in Julia is newer and less mature, but we hope it can be faster. It's strongly typed, and I know the code, in my opinion, is more visually pleasing. Both of them allow for batch programs for Jupyter notebooks, so that's nice. So I'm going to go through some basics. I mean, these are just very simple examples. So how to do basic quantum mechanics using this framework. Maybe you already have used QTIP or something like that, and then it's very similar. But anyway, just in case. And the example we're going to do is a hydrogen atom, ground state, energy levels. And so yeah, we have a proton, we have an electron with spin half, the proton with nuclear spin half. And so the spin basis, as we all know from our basic quantum mechanics, looks like this. And in Julia, we can create these bases, one for the electron and the other one for the proton, with this function spin basis. We can do it for any arbitrary spin that we like, which is nice. And it creates the basis for us. Here it's spin 1/2, and the double slash actually means that this is a rational number. So that's native to Julia. So that's also nice. You have these rational numbers like that. Of course, we have to combine these two bases to deal with both the electron and the proton. So we do that with the outer product here. And we'll get this result, that both spins up, down, up, and both down. It's 4-dimensional Hilbert space. And again, in Julia, so we've created the basis for the two, the electron and the proton, and we create the composite basis with a simple command, and it tells us what we have. And this is just one feature that I like. We'll see it again and again, how it tells us exactly what we have and keeps us sort of doing the right things. Then obviously we need operators, the Z component operator of the spin, and raising and lowering operators. Well, we know the formulas. We know how to measure spin. And of course, these are matrices, again. And we can define them. Julia has these functions, so sigma Z for the Z component, and sigma P for the raising operator, sigma M for the lowering operator. So we just give it the basis, and it creates the matrix for us. For example, here for SC, it tells us exactly what we have, a 2x2 operator. It tells us our basis, in this case, defining as a sparse matrix and whatnot, and the data that's stored in that operator. Again, and that helps us keep things straight and avoid errors, as opposed to just defining matrices on our own, and it allows us to use functions that already exist. So we have to define two more. Identity operator, also built-in function, and the angular momentum squared, which is simple. And again, the items are stored, and we have all the information that we need, and that keeps everything cleaner, in my opinion. So for the atom, we need these operators in the composite basis. So we have to again use the outer product with the identity times the electron spin operators, or the nuclear spin operators times the identity, and we get, on the left for electron spin, on the right for nuclear spin, the matrices 4 by 4, which again in Julia we easily make with these outer products with the tensor command. So it's just one line, and we get all these matrices just the way we would like, the way we'd expect. And finally, then we have to make our own. We have to build other operators ourselves. For example, dot product of nuclear and electron spin. So, well, we have our formula and we just apply it, and we get another matrix. Again, Julia keeps track of everything for us, and we know what we have. We know the data inside the matrix and the bases and the object type. And there we are. And we can change bases too, of course. This is more standard stuff. We're going to go from the uncoupled basis to the coupled basis. So we use the Clebsch-Gordan coefficients. I'm not going to go through the details, obviously, but we can calculate those easily using another package, Wigner-symbols.jl. So that makes it easy for us to calculate them. We create these transformation matrices of the Clebsch-Gordan coefficients. We can get the inverse. Again, Julia is great at matrix, any linear algebra stuff. It's really good at it. So that's easy. There's our inverse bases. And but then we don't just want matrices. We obviously want that to be an operator. So again, we define it as an operator. So we take the data that's stored here in C for the Clebsch-Gordan coefficients, and we have the left-hand basis and the right-hand basis. So, and that means, again, we have all the information here to help us avoid mistakes and to know what we have. That we have an operator, the dimension, the left-hand basis, the right-hand basis, and the data that's inside. And we can get the Hermitian conjugate easily too, just another command. So then we're ready to go from whatever basis we want to work in. So we can transform, for example, a state vector just using our transformation matrix, or we can transform another operator using the transformation matrix and its Hermitian conjugate. So basically, these are a lot of the things we want to do all the time in any kind of quantum mechanics problem, and we can do this in Julia. And it's nice. It can be used also for classwork, to illustrate some of these things and let students calculate them. So you can create Jupyter notebooks or Pluto notebooks or whatever you like. And I don't know. I think it has pedagogical potential. Much like Qtip, but I think the code is nicer and easier to follow, in my opinion. So now we're ready to calculate the Hamiltonian. So we have it here. We're going to ignore the nuclear spin part because it's really small. And well, in the uncoupled basis, the Z component operators are diagonal, but the dot product of nuclear and electron spin is not. But we've calculated earlier. As I said, we'll ignore the nuclear component, and so we get this Hamiltonian. And then now we just have to diagonalize it. We get eigenvectors and eigenenergies. Here we are defining the constants. There's actually a Julia package that allows you to put units on everything. I didn't do that here, but anyway, you can. The magnetic field is defined as a range because that's typically we want to calculate these functions for a range of magnetic fields. As in an experiment, we might scan the magnetic field. So we have a range which gives then our Larmor frequency a range, and then we have this. We define the Hamiltonian for each element in the range. We get the eigenstates, which gives us the eigenvectors and the eigenvalues for every element in the list. And that's all. We have our results, eigenvalues, eigenvectors, and we can plot them. We plot it, and it looks like what we want it to look like. So Zeeman effect for 1s level of hydrogen. So super simple, up to 1,000 Gauss or whatever you want. And we see here we're going to have mixing, obviously, of some levels. So these levels not mixed, other levels are mixed, and so it's nice that we can easily get the eigenvectors as well. So we can figure out what is the level of mixing, and we can check at B0 in the uncoupled basis. our vector is just pure, the lowest energy, this one, is just pure up, down, down, up. So we see right here. But, and we can transform it to the coupled basis, and then it's just the J0, M0 as expected. But if we go to higher magnetic fields, it's no longer pure in the coupled basis either. So we get mixing. So we can figure out exactly what that mixing is, and that's going to be important later on when we want to use have transitions between these states. Yeah. But two of the states, the up and totally down states, no, the ones that remain linear, so they remain pure even at high magnetic fields, as you can see. So just everything as we expect. So now we have to model the interaction with light. So we're going to look at the rate equations for Zeeman coherences. So we already looked at this, the internal atomic Hamiltonian and the magnetic field. Now we're going to have the light interaction. So we have to define the magnetic field as an oscillating function. And we're going to get a dipole operator between the one state and another, excited state and ground state. And we're going to use the density matrix to describe everything, which allows us to have both atomic coherences and also statistical ensembles all together. And here's the equation we're going to solve. So for the equation of motion of the density matrix, we'll just have the Hamiltonian commutator with the density matrix, and then we have a relaxation operator. And so here, again, we're going to start with a toy model here, just a 4-level system, J1 ground level, J0 excited level. We're going to have quantization axis along Z. The light polarization vector, electric field vector of the light is going to be perpendicular to that. So we can decompose the light into two circularly polarized components, sigma plus and sigma minus. And we can have some detuning, and we can have a Rabi frequency. And yeah, so we could solve this with the Liouville equations, which would give us a lot of equations. In this case, it doesn't matter so much. It's 16 versus 10, but anyway. Or we can work on those equations a bit and reduce them, eliminate the cross terms, the coherences, and just have leave the optical coherence and leave the Zeeman coherences. And that, in this case, gives us 10 equations. So it'll be simpler. For more complicated systems, we save more. And for that, we can calculate the fluorescence using this formula. Or we can also calculate the absorption of a probe. So we can define a probe with a different polarization or strength and define the absorption. So that's what we'll try to do. And here's what these rate equations look like, the simplified Liouville system, not so simple. Yeah, for the ground state and the excited state coherences. So we have a lot of terms for light absorption and emission. So all of them contain the dipole elements and then some density matrix elements. So yeah, so there's a whole bunch of them. Then we have spontaneous relaxation. So that's the big gamma that defines our spontaneous relaxation, and it goes in this simple system equally to all the ground states. For something more complex, obviously, we'd have to calculate the transition probabilities for each of those states. Then we have transit relaxation, so atoms flying out of the beam. So they fly out of all the levels, no matter what, at a rate gamma, proportional to the level population. And that's represented by little gamma here. And then we have repopulation. So again, in this case, they're coming in. We got to have this. We're going to keep the same number of atoms, so they got to fly in with little gamma divided by 3. And as I said, we assume that before atoms come in, they've hit the wall and they've relaxed to the ground state. If it were different, we can modify this system, obviously, to account for differences with that too. And then we have the destruction of the Zeeman coherences in this term here. So it's caused by the magnetic field. So okay, so that's these are our equations which have to be programmed. Whoops. Okay, here we are into Julia. again, this is a toy model, so they can be done by hand. If you have a more complicated system, it has to be automated. And we get this, these are the equations for the density matrix. So we have for the ground state, 3 by 3 system, and then the excited state is just one equation. And we don't have to solve anything on these states. That's where we start to, we can save a little bit of computing time, computing power. And so we define a function to compute these as a vector, this density matrix element is as a vector. And then we can solve, it just becomes a linear algebra problem, basically. Solve a steady, if we're interested in steady state, which is what we usually do. Not always, but usually. We can solve the steady state differential equation here. And we get our solution. We get the density matrix out for different values of the magnetic field. And we can, for example, get the ground state population, which is just the diagonal elements of the ground state part, or the excited state population, which is the diagonal element of the excited state part. We know the trace has to be 1, so that's a simple check we can do. And yeah, so we got a kind of a Hanley effect, narrow resonance right around 0. That, you know, this is let's say a typical experiment, you know, or magnetic field type measurement approach that we might do. And well, if we want to do this in cesium, obviously it's much more complicated. We have, you know, ground and excited states, and, you know, something we usually want to actually keep track of all levels, just in case. Also, we have Doppler, so we have to average over that, and that adds obviously a lot more computation. And well, we're going to have 64 by 64 matrix for the ground state, the same for the excited state in this case. And you know, for the rate equations, we'll have 128 by 128. Fluid will be even more. And yeah, and we can get here also these. This is our level structure that we looked at before. And, you know, we can calculate a similar situation, all kinds of situations that we might be interested in. Here we have, again, magnetic field along the z-axis, which usually is the quantization axis. It's whatever we want. And we have electric field perpendicular to that, electric field of the light vector, which is propagating in this case along x. It doesn't really matter, it doesn't enter into the equations which direction it's propagating. And here we're looking at fluorescence. And again, as a function of magnetic field, we get this kind of a system, and we can get, you know, pretty good agreement if we get the right parameters. And another thing we can do is we can look at the angular momentum probability distribution that's associated with the density matrix. Again, I won't go into the details, but here you have again the same kind of or similar cesium system. Let's say on the left we have the ground state. Nothing too interesting there for those conditions. Mostly stays the same. The excited state for linear polarized excitation. Well, for low field, you keep mostly this dumbbell shape. Doesn't get to move very far. Doesn't process very far before relaxing. But if we have a high magnetic field, then basically it's processing in the magnetic field and before relaxing, and we basically get this sort of torus or donut shape. And anyway, this gives some intuition, or can give some intuition to what's going on. It's also useful for dynamic problems to see how they're developing. So anyway, this is just a function in the package, and it's pretty simple to implement. It can be used also in these models. So our negative result is trying to model the Outler-Towns effect in alkali atoms. So here we had again a similar type of system. Differences are again we have cesium. 4-to-4 transition. Well, we looked at a whole bunch, but here's 4-to-4. We have a static magnetic field that we want to measure along the z direction. We have optical excitation with electric field vector parallel to that magnetic field, parallel to the z direction. And we have a RF field where the magnetic field with the RF field is perpendicular to this magnetic field direction. And so this is your standard optical RF double resonance setup. Also a way of measuring magnetic fields. Can be a way of measuring magnetic fields. So here is a magnetic field against transmission in arbitrary units. So when your RF frequency, or when the magnetic field corresponds to the Larmor frequency of the RF, the Larmor frequency and the RF frequency are the same, you get this peak. That's your way of measuring magnetic field. You get it on both sides of 0. And we looked at it increasing the strength of the RF excitation. And as it gets stronger, you get splitting. So this is a kind of Outler-Towns effect. So we thought that was kind of interesting because it's been studied before in our center, laser center, but not quite in this conditions. So we said, let's model it. So again, first we try a toy model, generic J1, J0 transition, which is what we saw mostly people doing. And yeah, so here's the Hamiltonian. We have our detunings and projection operator, optical excitation. So in this case, it's just delta M0 transition. And then we have the RF excitations between the magnetic sublevels, different Rabi frequencies, the optical and the RF Rabi frequencies. Excitation, in this case, we're not going to use the same program that I presented earlier. I mean, we're using Julia, but in this case, we just define all of the transitions, and then Julia makes the Liouville equations itself and solves the master equation itself. We also have to define relaxation through a Lindblad superoperator. So these are all very simply defined also in that Julia package for spontaneous relaxation and for fly-through relaxation. And yeah, this is the result. We got more or less qualitatively exactly what we want, different frequencies. So we thought, great. So now we can do it for 4 to 4. And it almost seemed like it worked. So here's our Hamiltonian. We got all the possible little transitions. And it looks really nice, except we were sort of cheating. I had to cheat. This is not the absorption. It looks very much like the experimental absorption signal, but it's actually just the population of the 4-0 excited state. So it can be made to look pretty good, which is kind of suspicious. But when we actually calculate the real absorption, summing over all the states, well, then the splitting disappears. It just disappeared. So something's wrong. And we couldn't figure out what until maybe recently. One of our students, he used a slightly different approach. Hopefully, it turns out to be correct. We will see. But anyway, so I guess the 2 lessons here are: one, the framework I described earlier was not so easy to convert into this RF. Was not so easy to convert the RF to that, so we had to sort of reprogram it. But then something was wrong. Something went wrong, which we still don't know quite why. Even though we hope to have found a solution using somewhat different methods. And yeah, in conclusion, so Julia and the quantum optics package are powerful tools for atomic physics computations. There are also applications to teaching using notebooks. And we can calculate energy levels, model absorption and fluorescence for atomic systems, at least the ones we usually work with. But yeah, there's always a tension in creating software to solve a particular problem and to have it be useful for more general situations. And finally, I'd like to thank my colleagues, our group leader, Professor Marta Sauzinch. Then also big thank you to Dace Osita. She was a master's student who did all of the programming, almost all the programming. And I don't think she would mind me saying that when she started her master's thesis, she was not, a big programmer. And so I think the fact that it worked is a testament, obviously, to her tenacity and her talent, but also that the Julia was not so intimidating, as the C code. We had a C code doing all the same stuff before, but that was just, we wanted something new and easier to deal with. So I think she did a great job with that. And now I'm sure she's a great programmer because she moved on to CERN to work on CMS. And then Laima Bushaita, Artus Moses, and Antons Nikolaevs. So thanks a lot for your attention.
Thank you. So we have 5 minutes for questions. Please. So if nobody of the attendees has a question, I have one. So you showed us that in the slides where you showed the resulting density matrix, the stationary density matrix. Of course, rightfully, you said you should check that the density matrix should be with the trace we expect it has. But I was curious if on the numerical side, is there some way to enforce the trace preserving property of the operators, or like to have a class of operators that preserve the trace, so you have it for granted? I'm curious about this, like on the numerical side.
That's a good question. I wonder if that's true for the operators. The problem here is this matrix is not the result just of operators. The operators that we use are making sort of tools for us to make elements of the calculation, like the energy levels and the eventually if when we get the level mixing. But then we have to define all these equations, and there, yeah, I mean that's a good way to find mistakes or introduce mistakes, as we define these equations. I don't know how to make it guaranteed. For us, it was a good diagnostic. Of course, it would be great if it could be enforced somehow, but I don't know the answer to that question. But that's great. Yeah.
I see. I mean, probably it's a good way to have a second check. To add some redundancy. So I see. Thank you. Any other questions?
Probably you want to know if Julia is the way to go or it's still Python. I don't know the answer to that question.
Experience with the QuantumOptics.jl package, but I used Julia for some Gauss-Pitayevsky, some extensive, let's say, Gauss-Pitayevsky equation solving for matter wave solitons. So I see how it's appreciated. So if no one else has a question, I have actually another curiosity. I would like to ask if you could spend some words on the physical approximations used for deriving the optical Bloch equation in the way that you use them, because you separate. Separate the ground state and the excited state, and you then work with Zeeman coherences. So I'd just like to ask if you can spend a few words.
Yeah, that's a good point. So let's see if I can show here. Maybe it's too small. There we go. So here are our assumptions for this, for going from the Liouville equations to the rate equations for the Zeeman coherences. So there's conditions on the spectral line width of the laser that it should be larger than the natural line width. That is probably not. And I should say these conditions are if you want to use that approximation for a time-dependent state. For what we usually do, which is the steady state. So these are not required, these conditions. But if you do want to do it time dependent, then they are required, and so that's something that one should be careful with, because the line width of the radiation is probably not going to be larger, at least for most modern lasers, than the line width of the transition. Then there's a condition of the mode spacing should be smaller than the natural line width, and the spectral line width should be larger than the characteristic evolution time of the density matrix. So I think if you want to use these equations for a time-dependent problem, you have to be very careful, or just go to the Liouville equations. But if you're going to do a steady state solution, then they shouldn't matter. So
I see. Thank you. So in the steady state, the situation, the assumptions are more relaxed. Let's say. I see. Okay, I think we have time for another question, if someone has it.
If none of the students have questions, maybe I can ask one. I've never used Julia myself. I've been always curious about it. I've heard that there is a way to do offloading onto GPU. Have you experimented with that and have an idea of like how fast it is compared to writing something in CUDA or SYCL or one of the
Yeah,
standards?
I haven't done it myself. I know there's a Julia package which they sort of advertise, a lot. Their CUDA.jl. I don't know. Suppose it should be powerful and easy, but I haven't used it myself. Yeah, that's an interesting thing because that's also one of the things we're thinking could be useful, because sometimes our calculations take a long time, so we want to use them either on a cluster to parallelize, or use it this way, but I haven't got around to it yet. Yeah. The student we have now, he doesn't like Julia. He likes Python. So, so we have kind of this issue.
Thanks.
I may try to give my side of an answer. I tried to use CUDA.jl for the Gross-Pitayevsky simulations, and I didn't run extensive benchmarks, but I think it's coherent to the rest of Julia. So if you wanted to prepare something that gives you computational advantages with the little let's say with not an extensive knowledge of GPU programming, etc. Like I don't have it. It's feasible, and I took it like a couple of days, and I got speed ups. But I didn't go too much inside of it. Just my point of view.
Thanks. Cool. That's encouraging.
Okay, so I think we can thank again the speaker for the nice presentation. And thanks also for highlighting one negative result. It's a precious opportunity to see, especially for the youngest of us, to see some actual research going on. So thanks again, and I think